Hello, today we're going to be talking about atmosphere and weather 1. We're going to continue this with 2 more lectures in the next couple of days. The Earth has an atmosphere. Atmosphere is, according to us, very, very thick, but compared to the size of the Earth, it's very, very thin. If you say that the Earth's diameter is 12,000 kilometers, the atmosphere is only 120 kilometers thick. Comparing this to an orange, if the orange was the size of the Earth was the size of the planet Earth, the atmosphere would only be 1 molecule thick on the surface of the orange. We basically have 2 major layers that we think about. There's other ones like the mesosphere, the ionosphere, but the 2 main ones we worry about are the stratosphere and the troposphere. The stratosphere is where the ozone layer is, and it's the one that blocks most of the high energy UV radiation. It allows some of the UV radiation that allows us to get suntanned, sunburned, but it also helps us produce vitamin D. The troposphere is where we live. It is where the weather occurs. It's where the pollution is. 72% of all air molecules are below the cruising altitude of commercial airlines, which is right at the border between the stratosphere and the troposphere at about 33,000 feet. The troposphere goes up about 5 to 9 miles, goes from 17 degrees where we are to minus 52 degrees up at the top. If you've ever been in an airplane and can touch the window, it's very, very cold. Why? Because it's minus 52 degrees. Almost all weather occurs in this region. Now, one of the things that we are very happy happens is something called the greenhouse effect. Greenhouse effect is where it gets warmer. Now, some of the things that you need to understand is that the light coming down is from the sun is UV, has UV radiation in it, which are right here. It has visible, which is from basically right here to right here, and infrared or heat that goes down this direction. Now, if you notice, vast majority of this high energy UV radiation right in here goes away because the ozone layer blocks it out. Some of the light is blocked out. For example, a lot of the blue. Why? Because it scatters in our atmosphere. That is why it appears to be blue, because it's scattering the blue light. And then some areas of red are removed also. Now, basically what happens is as the light comes down, all those come down, and some of them are not allowed through our atmosphere, and so they bounce up. So the UV radiation bounces, the ozone, a lot of the UV radiation bounces off, some of the visible and some of the infrared. The ones that come down through, the vast majority being visible plus infrared, they're absorbed by the ground. And when light is absorbed, it's re-emitted at a lower frequency. Now, that lower frequency is infrared. When it goes up, even though CO2, methane right in here did not stop the the visible, it does stop the infrared. And so what happens is the infrared is absorbed by the CO2, the water, the methane, and half of it is then re-emitted up, half of it is re-emitted down. And this keeps on happening over and over and over again until all the energy that initially came down from the sun has left the planet Earth. Now, there's various things that increase the greenhouse effect. Some of those things that increase the greenhouse effect are such things as, like I said, water, CO2, water, methane, CO2, and some other things. They naturally come from volcanoes and other things. Now, there are some things that decrease it. For example, clouds. Clouds block it out. Ice has something called the albedo effect, ice and snow, where the albedo effect means it comes down, and since it's white, it does not absorb any visible. If it doesn't absorb it, it reflects it off, and therefore it's not going to be re-emitting infrared. Now, we fortunately have seasons. If our axis was straight up and down, we would have one season, and that's it. However, we have seasons, and it's because of the tilt, 23.5 degree tilt of the Earth. Now, the reason that this happens is because this tilt of the Earth, the sun sends in rays, and by the time they get here, they are basically parallel to each other. Now, if you notice, right here where that hits, this is the same amount of light as this, same amount of energy. However, this just goes over a small area. This one right here almost goes over twice as much area. But it gets even worse. If we look down at the South Pole, there are areas down there where there is no light coming whatsoever. If there's no light, it's going to be very, very cold. That's why it's the Antarctic. Now, the opposite happens during our winter in the Northern Hemisphere, where it comes in, and notice how right at the equator, it's basically fairly close to each other all year long. So at the equator, it's basically the same season all the time. That's why meteorologists don't really don't work down there, because it's hot, humid, and raining all year long. Whereas here, during our winter, the North Pole has 1 to 2 months of darkness. Now, another thing that changes the temperature is the latitude. Now, people have trouble remembering the difference between longitude and latitude. Latitude is just like your hat. It fits on your head, and it goes across. Each latitude is a different distance around the planet Earth, going from all the way at 90 degrees latitude at the North and South Pole to 0 degrees latitude at the equator, which is huge. Areas over the equator are very, very warm, just like what we saw a few minutes ago, and polar regions are very, very cold because the light that hits them is spread out over a much, much larger area. That's called insolation. High latitudes, like I said, have very, very cold or moderately warm. There are times during the year, like the high latitudes during our summer, get 24 hours of sunlight. And then during our winter, they get 24 hours of nighttime. Now, one of the things that this does is it causes a very, very warm in this region, but as you go farther north, not only the land, but the ocean gets colder and colder and colder. And that causes differences in humidity and so forth. So it is much more humid at the equator, where it's very, very red, than what it is up in Alaska. Now, what this does is this imbalance has to be fixed, because the energy, we don't want the equator to get super, super hot. And so what's going to happen is that this energy is going to balance itself. And this is going to be seen in winds, water flow, where warm water is going to move towards the North Pole and South Pole. Why? Because it's less dense. It's going to go to the surface. Cold water is going to sink to the bottom, and it's going to be a conveyor belt, not just of the water, but of the air. One of the things we can see this, I'll show you this in the Hadley cells. Hadley cells is at the equator. We have very, very warm. Well, warm air rises. As it rises, it's going to get colder and colder and colder. Well, as that happens, it has a less ability to hold moisture. And so we're going to get tons and tons of precipitation down here. Okay. But this is traveling up. Air has to replace it. That's why going from north and south, there's air moving in this way. Well, it also has to come back down. And so at 30 degrees north and 30 degrees south, the air goes back down. Well, at this point in time, right here, it's very, very dry. And as it goes down, it gets warmer and warmer and warmer, getting drier and drier and drier. That's why places at 30 degrees north and south, like the Sahara or Saudi Arabia, are going to be deserts. Now, the other thing that happens is, this keeps on spinning. And so if we look at Vancouver, British Columbia, Washington State, they have temperate rainforest because it gets up here and there's a lot of rain. What's confusing to a lot of people is at 90 degrees north and 90 degrees south is a desert. Very, very little moisture coming down. Well, people always ask me, Dr. E, why is there so much ice in the Antarctic then? Well, the reason why is that ice has been up there for hundreds of thousands of years. Now, one of the things that happens is in there's something called the Coriolis. Within between 0 and 30, the air is going to spin. And this little video is going to tell you all about it. It's one of my favorite videos I show all year.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
And we will continue with the Coriolis effect tomorrow. Thank you.